This is a review of homework 12, which just involved one problem. So here's was a set of data. So we have hours of TV in relaxed mood, and we've got 4 participants, each of whom reported how much hours of TV they watched during the week, and then to what extent they were in a relaxed mood. And so there's basically 5 different parts of the problem, which is to first calculate the correlation coefficient, create a scatter plot of the data, and then using TV as X and mood as Y, calculate the unstandardized regression equation. Okay, so we're just going to use TV as a way to predict mood. And then using the regression equation calculated, what are the predicted values for 3, 4, 6, and 11, and then calculate R squared by determining sums of squares total and sums of squares error. And for these various steps, I had also given specific instructions for using the definitional formulas and using the formulas that I present in the lecture, because really there's no point in using more computational formulas. We have statistical software that will do this for us. And so the whole point of even doing these calculations by hand is to see where the numbers come from and to be able to understand the definition of the statistic by using the definitional formulas. So that's the whole point. So the first thing was to calculate the correlation coefficient. And so recall that to calculate the correlation coefficient, we have to find the sum of the cross products and then divide that by the number of pairs of scores. So the first step, what you had to do was just take hours of TV, convert to a z-score, do the same thing for relaxed mood. Okay, get relaxed mood to convert to a z-score. I've gone over this in previous reviews of homework and in lectures, so this is really just showing my numbers for you to be able to double check and to be able to review the process. But again, I really like to organize my work this way. I suggest that this is a good way for you to do it. So much so that on an exam, I will ask you questions in a way to see whether you're able to calculate it this way. Okay, so just fair warning. So once we determine Zx and Zy, we're just going to take the cross product of those two. Again, this is just literally taking Zx times Zy to get the cross product. We take the sum of the cross product, and then we divide the sum of the cross products by the number of pairs of scores, which is in this case 4, and that gives us our correlation. So correlation of 0.58, what we can see is that there is a strong positive association between the number of hours of TV that people watched and the extent that they report that they're in a relaxed mood. Create a scatter plot. So should have something like this. I also overlaid the regression line, or the line of best fit, but your scatter plot should look something like this. And in a scatter plot, it's a couple main things. It's important to properly identify the X variable and the Y variable. That is, what is the predictor and what's the outcome. That was given in the problem, so it should have been fairly straightforward that the X variable was TV, because I said that's the X variable. But to know that the X variable is plotted along the horizontal axis, the Y variable is plotted along the vertical axis, and that there's values of on both your X and your Y axis that make sense. Okay, and so why does it make sense that 0 is on both? Well, we didn't actually know how relaxed mood was reported, but so we can say, though, that 0 would mean not being in a relaxed mood at all, and it's possible to watch 0 hours of TV. So we're going to start our scatter plot really at the origin of 0 and 0. All right, so anyway, the scatter plot should look something like this, and it's just to reveal that we do have that positive association between those 4 data points. So the next thing that we're going to do is, using TV as X and mood as Y, calculate the unstandardized regression coefficient. Okay, so here's our prediction equation that we've been using. So we want predicted mood as a function of hours of TV, and we need our regression constant and our unstandardized regression coefficient. So we get that unstandardized regression coefficient by taking the correlation coefficient, multiplying that by standard deviation of y divided by standard deviation of x. Once we've got our b term, okay, our unstandardized regression coefficient, otherwise known as the slope, we use that slope term in our equation for a. We take the mean of y minus b times the mean of x. Oops, there's animations. Okay, so doing that, we had just previously calculated that the correlation is 0.58. We use the standard deviation of y that we calculated as well as the standard deviation of x that we calculated. So where does the standard deviation of y and the standard deviation of x come from? That should have been a part of your calculations right here. Okay, so our standard deviation of y and our standard deviation of x. So in calculating the correlation coefficient, you had to be able to get to the standard deviation of y and the standard deviation of x because you used that to determine your z-score. So you've got those quantities in order to help you calculate your slope term. So really all that information is right here. You just need to take your correlation coefficient, multiply it by standard deviation of y divided by standard deviation of x. It should be noted as well that when calculating the correlation coefficient, your standard deviation calculation doesn't need to be adjusted using the n-1 formula. You just divide, in this case, right here. So you're just dividing, in this case, by 4. All right. So there we go. So that's where those numbers came from. It's just a matter of plugging in and solving. So we get that b is equal to 0.42, which is directly interpretable. It means that for every 1 unit change in your predicted variable x, this is the associated change that you predict in y. So what it means is that for every additional hour of TV watched, we predict a change in y, in predicted mood of 0.42. Okay, or an increase in predicted mood of 0.42. Once we've got the b, we can plug in. Animations are a little funky here. Sorry about that. So where did the 6 and the 6 come from? Again, these were just values that you would have calculated for the mean of x and the mean of y in order to determine the correlation coefficient. So we've got mean of x is 6, the mean of y is 6. So plugging in, we get that the regression constant, otherwise known as the y-intercept, is 3.48. This is also directly interpretable. This is the value of y when x is 0. So we can say that when people watch 0 hours of TV, their predicted relaxed mood is 3.48. Okay, and so that yields our unstandardized regression equation where predicted mood is a function of the regression constant, 3.4, and then we're going to add the number of hours of TV times the unstandardized regression coefficient of 0.42. Okay. So the fourth part of the problem asks you to calculate the predicted values when people watch 3, 4, 6, and 11 hours of TV. And these were just the actual hours of TV from our little 4-person study here. Okay. So plugging in our regression equation that we just came up with, all we're going to do is just for hours of TV insert 3, 4, 6, and 11. Okay, so I've done that here for each of 3, 4, 6, and 11. Notice that the regression constant is exactly the same. The unstandardized regression coefficient is exactly the same, and we can see each of the predicted values. So notice that we do see some differences, right? So, let me get to that. Sorry, next graphic. So what we have is that for 3 hours of TV, we had the actual person in our study, and so the actual person in our study reported a relaxed mood of 5. Okay, but our regression equation that we will use kind of as like a generalization to predict to future people says, based on this correlation of data that generates our regression equation, which is just a straight line model, our predicted value for relaxed mood when hours of TV is 3 is 4.74. Okay, predicted relaxed mood, our y hat, is 4.74 when hours of TV is 3. What about when hours of TV is 4? Our y hat is 5.16. Notice that we've got some error, okay? Because in our actual study, the person that watched 4 hours of TV reported that their relaxed mood was 7. Our prediction for when hours of TV is 6, relaxed mood should be 6. Notice this is a very important principle, that our regression equation always passes through the mean of x and the mean of y. Okay, so any regression equation that you will calculate will always, this regression line will always, as in always, pass through the mean of x and the mean of y. Okay, so the predicted value of y when you're at the mean of x is the mean of y. And then last data point here, when hours of TV is 11, we get a predicted value of 8.1. You can see that there's a little bit of error. So the next thing that we want to do is we want to calculate R squared by determining sums of squares total and sums of squares error. So we want to evaluate how good is our regression model? How much, like what is the proportion of error that we reduce from using the mean? That's our interpretation. Another way of looking at R squared is, okay, so how much variability have we accounted for in relaxed mood by knowing something about how much TV that they watched over and above the mean? Okay, like how much variability are we accounting for in relaxed mood over and above the mean? So the way that we do that is we look at the difference between our actual 4 people and the actual mood that they reported, and the predicted mood based on our regression model, and we calculate the difference. So in this case, the person's actual relaxed mood was 5, our predicted mood was 4.74, so we've got a difference of 0.26. So for that particular data point, our regression model does a good job, which you can see right here. We were only off by 0.26. Okay, what about our second person here? So they watched 4 hours of TV, their relaxed mood was 7. Our model only predicted that when a person watches 4 hours of TV, the predicted mood should be 5.16. You can see that we were off by 1.84. So here we are, okay? So we're under predicting, so we missed this 1.84 here. There's 1.84 in error that we're kind of missing in our prediction. Okay. Similarly, we've got an error of -3 in this case at the mean. Okay, that's right here. So we over predicted in this case, and so we've got an error of, you can say like we'd have to subtract 3 to be accurate. That's the way of looking at it. Okay, and then here we are under predicting. So again, we've got a positive regression error right here of 0.9. Okay. Now, what you should see is when you sum up y minus y hat, when you just sum up these errors in prediction, you're going to get a sum that is exactly equal to 0, and that will happen for any regression line. Okay. For any regression line, those errors in prediction are going to balance out to be exactly equal to 0. We can almost kind of do it in our head here. If we add 0.26 and 1.84, we get 2.1. 2.1 plus 9 is 3, so positive 3 and then a negative 3 is 0. Those regression errors will always, always, always cancel out to 0. And that's why, in order to capture the total amount of error that we have, we've got to square those errors. It's a very similar principle to when calculating a variance around a mean, why we have to take the sum of the squared errors and not the sum of the errors. Okay, so that regression line functions just like a mean. And just like in calculating a variance around a mean, to calculate this amount of spread or error around this regression line, we have to take the sum of the squared errors. Okay, so that quantity is sum of squared errors. And then we get a number that is 13.27, which in and of itself is not immediately interpretable. This quantity, depending on the metrics that we're talking about, could be really small. Like if we're measuring something in millimeters, okay, and we're going to try to predict, like, you know, a distance in terms of millimeters or something like that, this quantity is going to be really small. Or maybe we're trying to predict somebody's income. The sum of squared errors is going to be really, really large. So we can't just look at that number and have that be immediately interpretable. What we need to do is evaluate, okay, if that's the amount of error that we have, how much error is possible? And the amount of error that is possible, in other words, sum of squares total, is what we get by looking at the overall variability in y, and that's what we would get if we would use the mean as our regression model. Okay. So our r squared is determined by taking the total amount of error that we would have if we use the mean. So this is just the sum of squares in y. So indeed, what we want to do is go back and use sum of squares y from our previous calculation for r. Okay, this is capturing the variability, the overall variability in y. That's the total amount that we could have if we just used the mean. Okay, and so when you go back and you look at that table, you should see that sum of squares total is 20. So that way, when we get our sum of squares error of 13.2, we can evaluate, all right, well, if this is the total amount of error, and this is the error that we have when using our model, let's look at the amount that we've reduced the total amount of error that we could have over the total amount. Okay, so this top quantity is really that reduction in error. If this is the total amount that we have, this is the amount that we now have, you can see that we've reduced that error. How much have we reduced that error? We're going to express that reduction as a proportion of the total amount in the first place. Okay, so what we can say is that instead of using the mean, we've reduced our error in prediction by approximately 34%. So these proportions can be interpreted as percentages. Okay, so we've reduced our error in prediction versus using the mean by 34%. Another way of saying that is that we have now accounted for 34% of the variability in relaxed mood by knowing how much TV somebody watches. We've accounted for, or we've explained about 34% of the variability above and beyond just using the mean. You should notice, of course, because we could just do the simple tactic of taking our original correlation coefficient 0.58 and squaring that. And if you just square 0.58, you should be able to, you should get a number very, very close to 0.3365. I think it's like 0.3364. Okay, so that's just a double check on your math. You can say, did I calculate r squared appropriately or accurately using this method? And you can check your math by just taking your correlation coefficient and squaring it, and those two numbers should be the same. And you might say, why in the world would I ever go through this long process of calculating the deviations and squaring the deviations and summing it up and then using this formula when I could just square the correlation coefficient? And the answer is so that you understand the principle. So that you understand the principle of being able to evaluate a regression model based on the sum of squared errors as a proportion of the total. Okay, that concept is not at all being able to look at this type of a figure and say, hey, is my model doing better than if I would guess the mean for everybody, right? So if we just overlay the mean of y, we've got this flat line. So am I doing better? Is my regression model doing better than the mean? So you can very clearly see here, if we use the mean here, we've got this much error. But if we use our regression model, we only got a little bit of error. If we use the mean here, we've got this much error. But we've only got this much error if we use mean, so et cetera, et cetera. So hopefully, by forcing you to do these calculations, the concepts, and it's the concepts that are really tested as well on the exam, that this will illustrate the concepts and really have it sink in why these statistics were created the way that they were, why the formulas are what they are, and ultimately what they capture. So it's not about just getting the number. Okay, it's really not about just being able to calculate a number because software does it for you. It's really about understanding the mathematics that goes behind the number And the way to really understand the mathematics is to understand it from a definitional standpoint, not just plug in numbers in formulas that, you know, there were computational, before the days of software, there were computational formulas that were created to simplify all this. Okay, so you've got definitional formulas and computational formulas. And the computational formulas were designed by people when they actually had to do calculations by hand. And they said, let's come up with a quicker way of being able to do the computations. But the computational formulas, it's not at all intuitive or clear why the formula is what it is or how it's designed to do what it does. That's why we use the definitional formulas, and that's why I give you examples where there's only like 4 people, so that the numbers are, it's small, it's straightforward, and you can see how it works. That's the point, which hopefully you're getting a better appreciation for. Okay, I think that's it. I'll get off that high horse, but just trying to illustrate a couple things. Hopefully this has reinforced a couple things, how to come up with, how, again, just how to calculate a correlation coefficient, how to take that correlation coefficient as well as the descriptive statistics, mean and standard deviation, and being able to come up with the slope as well as the y-intercept, okay, the regression coefficient and the regression constant, and then how we take that, the deviations or the errors from that regression line, we square those errors, we get a sum of squares errors, and then we can evaluate the regression line in comparison to the mean and say what proportion are we reducing our error in prediction by. All right, and that is it.